Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice exam that goes over redox reactions and electrochemistry. Let's go ahead and get started with problem number 1. Problem number 1 says, which of the following is not a use of sulfuric acid? A says extraction of phosphate. B says reactant in making important chemicals. C says light gas in neon signs, and D says paper production. To answer this, we need to think about what sulfuric acid is actually used for on an industrial scale. Sulfuric acid is one of the highest produced chemicals in the world because it's essential in manufacturing fertilizers, especially by extracting phosphate from phosphate rock. It's also widely used as a chemical reactant to make other important industrial products, and it plays a role in paper production during the pulping and bleaching process. Neon signs, however, are completely different. The glowing gas inside neon signs is not sulfuric acid at all. It's neon gas itself, which is a noble gas. Neon glows when it's excited by an electric current, and sulfuric acid doesn't play any role in producing that light. Therefore, the only option that's not a use of sulfuric acid is light gas in neon signs, which makes the correct answer C. Problem 2 says, which of the following is a major environmental concern associated with phosphate use? A says smog formation. B says greenhouse gas emission. C says algae bloom, and D says ozone depletion. Now, phosphates are heavily used in fertilizers and in detergents. When they wash into lakes and rivers, they act as a nutrient source for algae. With this excess nutrient supply, algae grows extremely rapidly on the water's surface. This is known as algae bloom. These blooms then block sunlight from reaching deeper water. They decrease oxygen levels, and then they can severely damage the ecosystem because of this. The other choices are not connected to phosphate use. Smog is associated with air pollutants like nitrogen oxides. Greenhouse gas emissions mainly involve carbon dioxide and methane. And then ozone depletion, that's driven by chlorofluorocarbons. None of these processes are caused by phosphate. Therefore, the major environmental concern that's associated with phosphate use is algae bloom, and that answer is C. Problem 3 says, what is the oxidation state of chromium in chromium oxide? The problem gives us the redox reaction. 14 hydrogen ions plus the dichromate ion produce 2 chromium 3 plus ions and 7 water molecules. The answer choices are +7, +3, +6, and +4. To figure out the oxidation state of chromium in the dichromate ion, let's first note that the overall charge of this ion is -2. This is going to be extremely important in the way that we work through this problem. Now we can look at oxygen and chromium because that's what makes up our dichromate ion. The oxidation state of oxygen here is -2. And we can confidently say that because this is not a peroxide and there's no fluorine present, which are the two main exceptions to assigning oxygen's oxidation number. So since this is not an exception, oxygen gets a -2 oxidation number. Now there are 7 oxygens total in this dichromate ion. The 7 oxygens contribute a total of -14. The 2 chromiums together need to balance this so that the total of the oxidation numbers comes out to -2, which is the charge of the overall ion. That means the 2 chromium atoms have to contribute plus 12 in total. When we divide that evenly across the 2 chromium atoms, each chromium has an oxidation state of plus 6. This also makes sense with the redox reaction shown because in the products, each chromium ends up as chromium 3 plus, meaning it's reduced from plus 6 down to plus 3. And that confirms that the oxidation state that we're starting off with is in fact plus 6. Therefore, the oxidation state of chromium in dichromate is plus 6, and that makes choice C the correct answer. Problem 4 says, what is the oxidizing agent in the redox reaction shown below? The reaction is solid iron reacts with vanadium 3 oxide to produce iron 3 oxide and solid vanadium metal. We're going to start by assigning oxidation numbers to every element in each substance. In elemental iron, the oxidation number of iron is 0. In vanadium 3 oxide, each oxygen has an oxidation number of -2. So the 3 oxygens are going to contribute a total of -6. The 2 vanadium atoms together have to sum up to plus 6 because this compound is neutral. So the sum of the oxidation numbers have to add up to 0. That makes each vanadium plus 3. In iron 3 oxide, each oxygen atom is still -2. So with the 3 oxygens here, we get a contribution total of -6. Since this compound is also neutral, the sum of the iron contribution needs to be plus 6. Therefore, we can say that each iron is plus 3. Finally, in elemental vanadium metal, the oxidation number of vanadium is 0. Now we step back and we compare reactants to products to see what changed. Iron goes from 0 in elemental iron to plus 3 in iron 3 oxide. This is an increase in oxidation number, and an increase in oxidation number means that iron lost electrons, so it is oxidized. Vanadium, on the other hand, goes from plus 3 in vanadium 3 oxide down to 0 in elemental vanadium. So this is a decrease in oxidation number. A decrease in oxidation number means vanadium gained electrons, so it is reduced. Oxygen here remains at -2 in both oxides, so oxygen is not undergoing redox here. Then, from these changes, we can name the agents. The substance that is oxidized, iron metal, is the reducing agent because it donates electrons. And the substance that is reduced, vanadium 3 oxide, that is the oxidizing agent because it accepts electrons. Therefore, the oxidizing agent in this reaction is vanadium 3 oxide, which makes choice B the correct answer. Problem 5 says, based on the reduction potentials, which species is the strongest oxidizing agent? The table lists fluorine gas with a reduction potential of plus 2.87 volts, iodine with plus 0.54 volts, silver ion with plus 0.80 volts, and zinc ion with minus 0.76 volts. An oxidizing agent is the species that gets reduced. So we look for the most favorable reduction. On a reduction potential table, the larger the reduction potential, the more easily that species gains electrons and gets reduced. And that means that it's going to behave as a stronger oxidizing agent. So, comparing the numbers, fluorine gas at plus 2.87 volts is the largest and therefore the easiest to reduce. Iodine and silver ions are positive, but they're smaller in value. And zinc ion has a negative value, meaning its reduction is not favorable under standard conditions. So the strongest oxidizing agent in this list is fluorine gas because it's the easiest to reduce, and we figured that out by looking for the largest reduction potential. The correct answer is A. Problem 6 says, what is the sum of these stoichiometric coefficients when the following reaction occurs in neutral water is balanced? The reaction is solid silver reacts with aqueous iron 2 plus ions to produce aqueous silver 1 plus ions and solid iron. So we're going to balance this using our half reaction method, and then we're going to be able to add the coefficients. First, we will assign oxidation numbers to see what changes. In the reactants, silver starts as elemental silver, and its oxidation number here is 0. It ends up as silver 1 plus in the products. Its oxidation number there is plus 1. So we go from 0 to plus 1, which is an increase in oxidation number. That tells us that silver loses electrons and gets oxidized. What about iron? Iron starts as iron 2 plus. That means its oxidation number in the reactants is plus 2. Then it ends up as elemental iron in the product with an oxidation number of 0. Going from plus 2 to 0 is a decrease in oxidation number, which means iron gained electrons and is reduced. Now we can write the two half reactions. So for oxidation, we can write silver metal forms silver 1 plus ions and it releases 1 electron. For reduction, we can write iron 2 plus gains 2 electrons to form iron metal. To balance electrons, we need to find the least common multiple between 2 and 1, which is just 2. Therefore, we need to multiply our oxidation half reaction by 2. So the oxidation half reaction becomes 2 silver atoms form 2 silver 1 plus ions and 2 electrons. Now our electron count in both half reactions match, and that means we can combine them together and the electrons cancel out and we get our reaction. It gives us our overall balanced reaction of 2 silver atoms react with 1 iron 2 plus ions to produce 2 silver 1 plus ions and 1 iron atom. Because the solution is in neutral water, no extra hydrogen ions or hydroxide ions or water molecules are needed to balance this. So from this balanced reaction, we can just go ahead and start adding up the coefficients to answer this problem. The coefficients are 2 for silver, 1 for iron 2 plus, 2 for silver 1 plus, and 1 for iron. So adding them gives us 2 plus 1 plus 2 plus 1. That gives us a total of 6. Therefore, the sum of these stoichiometric coefficients is 6, and the correct answer is C. Let's move on to problem 7. Problem 7 says, what is the total sum of all stoichiometric coefficients, including both reactants and products, when the following reaction is balanced in acidic solution? The reaction is permanganate ion reacts with iron 2 plus ions to produce manganese 4 oxide and iron 3 plus ions. We're going to again balance this with the half reaction method, and then we're going to add the coefficients. In addition here, since this is occurring in acidic conditions, we can add water and hydrogen ions to balance anything that's unbalanced, like oxygens and hydrogens. First, we're going to assign oxidation numbers to see what changes. In the permanganate ion, manganese is bonded to 4 oxygens. Oxygen here has an oxidation number of -2. So the 4 oxygens contribute a total of -8. Because the overall charge of permanganate is -1, manganese must be +7 so that the sum of oxidation numbers equals the charge -1. In the product, manganese 4 oxide, there are 2 oxygens at -2 each for a total of -4. Now this compound is neutral overall, so manganese must be +4. This tells us that manganese goes from +7 down to +4, so it gains 3 electrons. That means manganese is reduced. Now we're going to look at iron. Iron 2+ ions have an oxidation number of +2. And in the product, iron 3+ has an oxidation number of +3. That means iron increases its oxidation state from +2 to +3. That indicates to us that it's lost an electron and is oxidized. Now we can write the 2 half reactions. For the reduction half reaction, permanganate is becoming manganese 4 oxide, and it must gain 3 electrons. For the oxidation half reaction, iron 2+ becomes iron 3+, and it gives off 1 electron. To make the electron transfer equal, 3 electrons must be lost in total. So I'm going to multiply the iron half reaction by 3. That gives 3 iron 2+ ions forming 3 iron 3+ ions and 3 electrons. Now the electrons in both the reduction half reaction and the oxidation half reaction match. And when we sum up these 2 half reactions, the electrons cancel out. Once those electrons are matched and we add the 2 half reactions and they cancel out, we're left with the following reaction. We have permanganate plus 3 iron 2+ yields manganese 4 oxide plus 3 iron 3+. We now want to balance the remaining atoms in acetic solution. Manganese is balanced on both sides. That's good. Then on the reactant side, there are 4 oxygens total coming from permanganate. And the product side, there's 2 oxygens coming from manganese 4 oxide. To balance this, we're going to need to add 2 water molecules to the product side to supply the missing oxygens. So that introduces 4 hydrogens on the product side. How do we then balance that? This is easily done because we can go ahead and add 4 hydrogen ions to the reactant side to balance hydrogen atoms on both sides. In addition, you'll notice that iron is balanced on both sides. We have 3 iron atoms on the reactant side, 3 iron atoms on the product side. So our final balanced reaction is 4 hydrogen ions plus a permanganate ion and 3 iron 2+ ions. Those all react to form 1 manganese 4 oxide plus 2 water molecules plus 3 iron 3+ ions. The coefficients are 4, 1, 3, 1, 2, 3. Adding them together gives us a total of 14. Therefore, the sum of these stoichiometric coefficients is 14, which makes choice B the correct answer. Problem 8 says, what is the total sum of all stoichiometric coefficients, including both reactants and products, when the following reaction is balanced in a basic solution? The reaction is solid copper reacts with nitrate ion to produce copper 2+ ion and nitrogen dioxide. We're going to balance this with the half reaction method, and then we'll add the coefficients. Now, since this reaction occurs in basic conditions, we're allowed to use water and hydroxide ions to balance. But we're going to start by assigning oxidation numbers first to see what changes. Copper begins as elemental copper, so it's going to have an oxidation number of 0. It ends on the product side as copper 2 plus ions. Its oxidation number there is +2. So we're going from 0 to +2. This is an increase in oxidation number. It indicates to us that copper loses 2 electrons and is oxidized. Then in nitrate, nitrogen is bonded to 3 oxygens. Oxygen here has an oxidation number of -2. There are 3 oxygens total, so that means it contributes a total of -6. Since the overall ion charge is -1, nitrogen must have an oxidation number of +5. Then we can look at nitrogen dioxide. Each oxygen is -2 for a total of -4. That means nitrogen must be +4 since nitrogen dioxide is overall neutral. Then we can say that nitrogen goes from +5 down to +4. This is a decrease in oxidation number, and it indicates that nitrogen gains an electron and is reduced. Now we can write the 2 half reactions. For the oxidation half reaction, copper becomes copper 2 plus, and it releases 2 electrons. For the reduction half reaction, nitrate gains an electron to become nitrogen dioxide. From these 2 half reactions, we want to make sure that the electrons match up. That requires us to find the least common multiple of 2 and 1, which is 2. So we multiply the nitrate half reaction by 2. The electrons now match, so when we add the 2 half reactions together, we're going to get copper and 2 nitrate ions produce copper 2 plus ions and 2 molecules of nitrogen dioxide. At this point, it becomes important to balance oxygen in basic solution. Copper and nitrogen are balanced. It's just oxygen that we're concerned about. In fact, the products are short 2 oxygens compared with the reactants. The reactants have 6 oxygens and the products have 4. To fix this, we're going to add water and hydroxide in the appropriate amount and on the correct sides. We're going to add 2 water molecules to the reactant side and 4 hydroxide ions to the product side. Now we have 8 oxygens on both sides and 4 hydrogens on both sides. So this simultaneously balances oxygen and hydrogen under basic conditions, and it keeps the charge consistent. So the final balanced reaction is 1 copper atom and 2 nitrate ions together with 2 water molecules react to form 1 copper 2 plus ion, 2 molecules of nitrogen dioxide, and 4 hydroxide ions. The coefficients are 1 for copper, 2 for nitrate, 2 for water, 1 for copper 2 plus, 2 for nitrogen dioxide, and 4 for hydroxide. Adding them together gives a total of 12. Therefore, the sum of these stoichiometric coefficients is 12, and the correct answer is A. Problem 9 says, which of the following statements is true for the electrolytic cell? The statements given are: electrons flow from the cathode to the anode, the redox reaction is spontaneous, and oxidation occurs at the cathode and reduction occurs at the anode. So let's work through each statement. Let's think about electron flow. In any electrochemical cell, electrons always travel from the site of oxidation to the site of reduction. Oxidation happens at the anode and reduction happens at the cathode. That means electrons flow from the anode towards the cathode, not the other way around. Statement 1 says the opposite, so statement 1 is false. Next, we're going to consider spontaneity. By definition, an electrolytic cell uses electrical energy from an external power source to force a chemical reaction that would not happen on its own. Because it must be driven by a power supply, the redox reaction is non-spontaneous. Therefore, statement 2 is also false. Finally, let's look at the locations of oxidation and reduction. The rule, oxidation at the anode and reduction at the cathode, is always true regardless of whether the cell is galvanic or electrolytic. Statement 3 incorrectly reverses these assignments, so statement 3 is also false. Since all 3 statements are incorrect, the correct answer for this problem is D, none of the above. Problem 10 says, the shorthand notation below describes a galvanic cell. What occurs at the cathode? The notation is written as magnesium solid, single line, magnesium 2 plus aqueous, double line, silver plus aqueous, single line, silver solid. In this line notation, the left-hand side is the anode compartment and the right-hand side is the cathode compartment. A single vertical line separates phases within one half cell, and the double vertical line represents the salt bridge between the two half cells. Because the left side is the anode, oxidation takes place there. Magnesium metal loses electrons to become magnesium 2 plus. Because the right side is the cathode, reduction takes place there. Silver plus ions gain electrons to become silver metal. Therefore, at the cathode, silver is reduced. And the correct answer is going to be D. Silver is reduced. Problem 11 says a molten solution of sodium chloride and potassium bromide undergoes electrolysis. What is happening at the anode? The choices are chlorine gas is produced, bromine gas is produced, sodium metal is formed, and potassium metal is formed. To solve this problem, we're going to split these salts into their ions, sort into oxidation versus reduction, compare potentials, and then decide the products at each electrode. First, we break the salts into their ions. The molten mixture contains sodium ions and chloride ions from sodium chloride, and potassium ions and bromide ions from potassium bromide. Because this is molten salt, there's no water present to compete, so only these ions participate. Next, we assign which side each type of ion prefers. In electrolysis, cations are reduced at the cathode, and anions are oxidized at the anode. That means sodium ions and potassium ions compete for reduction at the cathode, while chloride ions and bromide ions compete for oxidation at the anode. Now we compare tendencies using standard potentials from the table. For the cations, which undergo reduction at the cathode, the reduction potentials are sodium ion to sodium metal at negative 2.71 volts, and potassium ion to potassium metal at negative 2.93 volts. The more positive reduction potential is easier to reduce, so sodium ion is reduced more easily than potassium ion. Therefore, sodium metal forms at the cathode. For the anions that undergo oxidation at the anode, we can write the reduction potentials as listed and then flip the signs so we have the values in terms of oxidation. Chlorine has a listed reduction potential of plus 1.36 volts for chlorine gas to chloride ions. So the oxidation potential for chloride to chlorine gas is negative 1.36 volts. Bromine has a listed reduction potential of plus 1.09 volts for bromine gas to bromide ions. So the oxidation potential for bromide to bromine gas is negative 1.09 volts. The easier oxidation is the one with the larger or less negative oxidation potential. Between negative 1.36 and negative 1.09, bromide is easier to oxidize. Therefore, at the anode, the bromide ions are oxidized to bromine gas. The correct answer choice is that bromine gas is produced, which is answer choice B. Let's move on to problem 12. Problem 12 says, using the table of standard reduction potentials provided to you, which of the following statements is true? We read the table by remembering that species at the top with more positive reduction potentials are easier to reduce and therefore strong oxidizing agents as reactants. Species at the bottom with very negative reduction potentials are easier to oxidize and therefore strong reducing agents as products. With that in mind, we can go through each option one by one. The first statement says that coinage metals are found in the lower left portion of the table. This is not correct. The coinage metals, such as copper, silver, and gold, have very positive reduction potentials, so they appear towards the upper right. The second statement says that strong reducing agents are found in the upper right corner of the table. This is also incorrect. Strong reducing agents sit low on the table where their reduction potentials are very negative, which makes them easy to oxidize. This third statement says that weak oxidizing agents are found in the upper left corner. This is also incorrect. The upper portion of the table contains the strongest oxidizing agents, not the weakest ones. The final statement says that metals that prevent rust are found in the lower right corner of the table. This is the correct description. These metals, such as zinc and magnesium, act as sacrificial anodes because they oxidize more easily than iron and therefore protect it from rusting. They occupy the region with very negative reduction potentials. Therefore, the true statement is D. Metals that prevent rust are found in the lower right corner of the table. Moving on to problem 13. Given the two standard reduction potential half reactions, what is the standard cell potential for a battery? These are the two reactions we're given. Zinc 2 plus gaining 2 electrons to form zinc metal. It has a potential of negative 0.76 volts. And then we have silver plus gaining 1 electron to form silver metal, and it has a potential of plus 0.80 volts. We have to decide which half reaction runs as a reduction and which one has to be reversed to run as an oxidation. The larger and the more positive reduction potential occurs for silver. So at the cathode, silver plus is reduced to silver. The zinc half reaction will therefore run in reverse at the anode. Now, to compute the standard cell potential, we're going to use our equation E naught cell equals E naught cathode minus E naught anode. And here, we're just going to plug our reduction potentials directly into this equation. We're not going to change the sign for anything. The minus sign in this equation takes care of that for us. So we can write that E naught cell equals plus 0.80 volts minus negative 0.76 volts. And that gives us positive 1.56 volts. Therefore, the standard cell potential for the battery is positive 1.56 volts. That aligns with answer choice A. Problem 14 says, what does a value of Q equal to 0.5 suggest about a battery according to the Nernst equation? Now, to interpret this correctly, we have to remember what Q represents. The reaction quotient Q is the ratio of products over reactants. And when Q is less than 1, that means the denominator is larger than the numerator. So there are more reactants than products present at that moment. Now we can connect that to the Nernst equation. The Nernst equation tells us that the actual cell potential equals the standard cell potential minus a correction based on the log of Q. If Q is less than 1, then log Q is a negative number. Subtracting a negative number is the same as adding. So the value of E cell becomes larger than the standard value for E cell. This makes sense chemically. When there are more reactants available than products, the reaction has a stronger drive to move forward, which makes the battery produce a higher voltage than its standard rating. So a value of Q equals 0.5 means there are more reactants than products. And because of that, the actual cell potential is greater than the standard cell potential. Therefore, the correct conclusion is that E cell is greater than E naught cell, which is answer choice D. Problem 15 says, use the Nernst equation to determine the difference in cell potential for an electrochemical process in which N equals 2 and Q equals 10 to the minus 2. We're going to start here by interpreting the value of Q. A reaction quotient of 10 to the minus 2, that's less than 1, which means there are more reactants than products. When there are more reactants available, the reaction is pushed forward more strongly, and the cell potential becomes larger than the standard value. Now we apply the Nernst equation. The correction factor is 0.06 divided by N multiplied by the log of Q. Since N is 2, the base correction becomes 0.06 divided by 2, which is 0.03 volts. The log of 10 to the minus 2 is negative 2. Multiplying 0.03 by negative 2 gives negative 0.06. In the Nernst equation, we subtract this term. So subtracting a negative number increases the cell voltage by plus 0.06 volts. Therefore, compared to the standard cell potential, the actual E cell increases by 0.06 volts. So that means the correct answer here is B. Problem 16 says, a battery with a 3-electron process reaches equilibrium with K equal to 10 to the 15th. What is the standard cell potential? To answer this, we need to remember the connection between the equilibrium constant and the standard cell potential from our lectures. When a reaction reaches equilibrium, the actual cell potential drops to 0 because there is no more driving force left. At that point, the entire tendency of the reaction to proceed forward is contained in the value of K, and we can extract the standard voltage directly from it. The relationship is that the standard cell potential equals 0.06 volts divided by the number of electrons transferred, N, multiplied by the log of the equilibrium constant, so log K. Here, the number of electrons transferred is 3, and the equilibrium constant is 10 to the 15th. The log of 10 to the 15th is 15, and 0.06 divided by 3 gives 0.02. Now we multiply 0.02 by 15, and that gives us 0.3. Because the equilibrium constant is extremely large, the reaction is strongly product favored, and that corresponds to a positive standard voltage. Therefore, the standard cell potential for this battery is 0.3 volts, which is answer choice A. Problem 17 says, suppose 12,000 coulombs pass through a solution of copper 2+. How many grams of copper are produced? To answer this, we treat this as an electroplating stoichiometry problem where electrical charge is being converted into moles of electrons and then into moles of metal deposited. We're going to begin by remembering that 1 mole of electrons corresponds to 96,485 coulombs. This value is called Faraday's constant. So the first step is to convert the 12,000 coulombs of charge into moles of electrons. When we divide 12,000 by 96,485, we get about 0.124 moles of electrons. Next, we look at the reduction that's occurring. Copper 2+ gains 2 electrons to become copper metal. That means for every 1 mole of copper metal that plates out, 2 moles of electrons are required. So to find the moles of copper produced, we divide the moles of electrons by 2, and that gives us 0.062 moles of copper metal. The final step is to convert moles of copper into grams using its molar mass. The molar mass of copper is about 63.5 grams per mole. So when we multiply 0.062 by 63.5, we get about 3.9 grams, which rounds to 4 grams. Therefore, the mass of copper produced is 4 grams, and that matches answer choice A. Problem 18 says, given the galvanic cell written in standard notation, how many grams of aluminum are depleted from the anode if the silver cathode increases in mass by 108 grams? So we're going to begin by reading the shorthand that's provided to us. Aluminum solid is in contact with aluminum 3+, double line. Silver plus is in contact with silver solid. In this notation, the left side is the anode compartment and the right side is the cathode compartment. That tells us aluminum is the anode and it is oxidized, while silver is the cathode and it is reduced. Next, we're going to write the half reactions. At the cathode, silver ions gain 1 electron each to become silver metal. At the anode, aluminum metal loses 3 electrons to become aluminum 3+. The least common multiple of the electron counts is 3, so we're going to multiply the silver half reaction by 3. Then we add these 2 half reactions, and we notice that the electrons cancel. What we have is that 1 atom of aluminum reacts with 3 silver ions to produce 1 aluminum 3+ ion and 3 atoms of silver. This tells us how the stoichiometry of silver and aluminum relate. 3 moles of silver correspond to 1 mole of aluminum. With that, we can set up the proper dimensional analysis calculation so that we can solve this problem. We begin with the 108 grams of silver that appeared on the cathode. The first thing we do is convert this mass of silver into moles of silver because the redox stoichiometry is based on moles, not grams. We do that by dividing by the molar mass of silver, which is about 107.9 grams per mole. So we write that down, 107.9 grams per mole. Once we have moles of silver, we can then use the mole-to-mole ratio from our balanced reaction to get moles of aluminum. This ratio is 3 moles of silver to 1 mole of aluminum. Finally, we can multiply by the molar mass of aluminum, which is approximately 27 grams per mole, to find the corresponding mass of aluminum that's lost from the anode. And this is going to give us approximately 9 grams of aluminum. So 9 grams of aluminum are depleted from the anode, and the correct answer here is A. Problem 19 says, the standard potential of a battery is positive 1.50 volts. If the reaction transfers 3 electrons, what is the standard change in Gibbs energy? So here we're going to connect voltage to Gibbs energy using this equation. The standard change in Gibbs free energy equals negative N times Faraday's constant times the standard cell potential. We can plug these values in and calculate. So the reaction moves 3 moles of electrons. That's given to us in the question step. Faraday's constant is about 96,485 coulombs per mole of electrons. And the standard cell potential is 1.50 volts. Again, that's given to us in the question step. Multiplying these together gives the energy the battery can deliver. So 3 moles of electrons times 96,485 coulombs per mole times 1.50 volts. A coulomb times a volt equals a joule. So the units convert directly to joules. The product is about 434,000 joules. Because the equation carries a negative sign for a spontaneous battery, the Gibbs energy change is negative. So what we have as our answer is negative 434,000 joules. We can rewrite this in units of kilojoules. We notice the answer choices are all in units of kilojoules, which is what's going to push us to doing that conversion. Negative 434,000 joules is equal to negative 343 kilojoules, which means the correct answer is C. Problem 20 says, which statement about the metal activity series is true? Before we look at each option, let's go over the general trend of the metal reactivity series. The most reactive metals are the alkali metals like sodium and potassium. These metals are so reactive that they'll even react with cold water. One step down in reactivity, we have the alkaline earth metals such as magnesium and calcium. These metals are still quite reactive, but they require hot water or steam instead of just cold water. Below that, in the middle of the series, we find the transition metals such as iron and zinc. These metals don't react with water at all, but they will react with acids. Finally, at the bottom of the activity series, we find the least reactive metals, often called the coinage metals, including copper, silver, platinum, and gold. These metals are so unreactive that they don't react with either water or acids, and they can't displace more reactive metals from their compounds. Now, let's go through each option, keeping this trend in mind. A says that gold will displace magnesium chloride. Gold is one of the least reactive metals, and magnesium is far more reactive. So no, gold cannot displace magnesium from its compound. This option is false. B says that platinum would react in hot water. Platinum is also one of the least reactive metals, and it doesn't react with water under any conditions. So this option is also false. C says that zinc will react in cold water. Zinc is a transition metal, and transition metals do not react with water at all. They react only with acids. So yet again, this option is false. D says that potassium would react in cold water. Potassium is an alkali metal, which is at the top of the activity series. Alkali metals, they react rapidly in cold water. This is the correct statement. So question 20 is D. Question 21 says, which of the following is not part of a lithium-ion battery? We have lithium oxide, graphite, porous separator, and lead oxide. In a lithium-ion battery, the anode is typically made of graphite. The cathode is usually made from a lithium-containing metal oxide, such as lithium cobalt oxide or lithium iron phosphate. Between the anode and the cathode, there's a porous separator that allows lithium ions to move back and forth while preventing a direct electrical short between the electrodes. Lead oxide, however, is not used in lithium-ion batteries. Lead oxide is the active material in a completely different type of electrochemical cell, the lead-acid battery, which is commonly used in car starter batteries. And since lead oxide belongs to lead-acid batteries and not lithium-ion batteries, it is the choice that doesn't belong. So the correct answer is lead oxide, D. Problem 22 says, which of the following is not a secondary battery? Lead acid, zinc air, nickel, cadmium, and lithium ion. Okay, to understand this question, we have to make the distinction between primary and secondary batteries very clear. A secondary battery is a rechargeable battery, and it can undergo many charge-discharge cycles because its redox reactions are reversible. In contrast, a primary battery is not rechargeable. Once the chemicals are consumed, the battery is dead and it cannot be restored. Keeping that in mind, let's go over the options. A lead-acid battery is rechargeable. It's used in cars, and it can be recharged many times as the alternator restores its charge. Nickel-cadmium batteries are also rechargeable, and they have been widely used in portable electronics and power tools. Lithium-ion batteries are yet another example of a secondary battery. They're found in phones, they're found in laptops, they're found in electric vehicles, and they are designed for repeated cycling. Zinc air batteries, however, are not rechargeable under normal conditions. They are primary batteries. They're commonly used in hearing aids and other small medical devices. The reaction that produces electricity in a zinc air cell, it's just not easily reversed, so they can't be recharged like the other three. Therefore, the zinc air battery is the one that's not a secondary battery. Problem 23 says, the metal used as a sacrificial anode should have blank. A says a higher reduction potential than the protected metal. B says a lower reduction potential than the protected metal. C says the same reduction potential as the protected metal. And D says a neutral potential. The job of the sacrificial anode is to oxidize first and take the corrosion on itself so that the protected metal remains in its reduced metallic state. A material that oxidizes easily is a strong reducing agent. On the reduction potential table, strong reducing agents sit low with more negative reduction potentials. Therefore, the sacrificial anode should have a lower or more negative standard reduction potential than the metal we want to protect. And that placement guarantees the sacrificial metal gives up electrons first and corrodes instead of that protected metal. So the correct choice is a lower reduction potential than the protected metal. So answer choice B. Last but not least, problem 24 says, below is the balanced equation for making aspirin. What is the atom economy of this process? We're told the molar masses. Salicylic acid is 138 grams per mole. Acetic anhydride is 102 grams per mole. Aspirin is 180 grams per mole. And acetic acid is 60 grams per mole. Atom economy measures how much of the reactant mass ends up in the desired product. The rule is take the molar mass of the desired product and then divide by the total molar mass of all of the reactants, and then you'll multiply that fraction by 100%. So here, the desired product is aspirin. Its molar mass is 180 grams per mole. The total mass of the reactants is 1 mole of salicylic acid plus 1 mole of acetic anhydride. So 138 plus 102, which equals 240 grams per mole. Now we're going to compute the ratio. 180 divided by 240 is 0.75. And then we multiply that by 100%, we get 75%. Therefore, the atom economy of this aspirin synthesis is 75%, and the correct answer is A. And with that, we've completed our practice exam. I hope it was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.